When we developed these equations of motion, we made the assumption that the coordinate system was aligned with what are called the stability axes. So that means that if I had my aircraft here, if it was flying, whatever direction it was flying in, we drew a vector from the center of gravity towards that direction that it was moving in, and we made that the body fixed x coordinate, or the x-axis. And then y comes out the right wing, and z comes out the bottom of the aircraft, perpendicular to the x-axis. So all of our derivatives, when we then went through our force and moment derivatives, and I've copied them down here just for reference, but each of these derivatives we needed to evaluate at this equilibrium state. And so we took the derivative, for example, of the aerodynamic or the pseudo-aerodynamic x force with respect to u. And it turns out that because we had aligned the x-axis with the free stream, that was similar to taking the derivative of the drag force with respect to u. And so when we non-dimensionalized each of these derivatives and plugged them into our equations, we ended up with derivatives like this, like derivatives in drag with respect to alpha hat, with respect to mu hat, with respect to q bar. But really, those are derivatives in the x direction with respect to mu, alpha, q, each of these parameters. So really, these derivatives that we've plugged in here are only true if our coordinate system is aligned with the free stream velocity here, or in other words, with these what we call the stability axes. Okay, so often we will get derivatives, aerodynamic derivatives, but want to apply them now to a different flight condition. So we may want to look at the aircraft at a different angle of attack. Maybe it's in climbing flight. Maybe it's just at a different velocity. If we slow down, for example, we're going to increase our angle of attack, but we can still trim at a lower velocity. And we may just have these derivatives that we've talked about here at a different flight condition, or at a different coordinate system. So what we want to do is now transform each of these derivatives so that we can use, we don't need to recompute these derivatives in our new coordinate system. We can actually take the derivatives from our original coordinate system and use them in a new coordinate system. Okay, so this is what we're calling the transformation of stability axes. And so I'm just going to write here, so we have our original xb coordinates and zb, and remember those originate at the center of gravity. And let's say now we're flying at a different angle of attack than this reference state. Now this original one, I'm going to call that my reference state. Okay, so you'll hear me refer to that as the reference state. But we may be operating at a different angle of attack. So we're going to call that our operating condition. And I'm just going to draw this other coordinate system here, and we're going to call that xb prime. That's our operating angle of attack. Okay, and so this has now been rotated. This is going to be zb prime. That will be rotated from our original xb by some angle phi. Okay. So originally we had computed aerodynamic derivatives. For example, we might have computed, let's say CL P bar, for example. That's a change in rolling moment with respect to rolling rate. So that would have been something around this axis here. That's my roll axis. And I'll just denote that L. But when we want to know CL P bar around this new axis, L prime, that actually depends on my not only my old roll axis, but also the information from my old yawing axis. So this was n, and right here is n prime. Okay, so basically before I needed a derivative, or originally I had a derivative in my rolling moment with respect to rolling rate about this axis, but now I need to know the derivative in rolling moment with respect to rolling rate about this axis, and it's going to depend on what my original yawing moment with respect to yawing rate was here, because this axis is now at an angle to my original roll axis and now has a component of that original yaw axis. Of course, my new yaw axis is perfectly perpendicular to my new roll axis, so those are somewhat independent, or I'm going to have derivatives about each of those axes, but the derivatives about these axes depend on the derivatives about the original axes. They're going to couple from this transformation, okay? So let's just work through an example here. So if I have a vector in, so we're going to just call this vxb, vyb, and vzb. So I've got some vector in my original body fixed coordinate system. I can multiply it by a transformation matrix here, which would be cosine phi 0 minus sine phi 0, 1, 0, and sine phi 0 cosine phi. And that will give me the vector. I should move this. That will give me the vector in the new prime system, or my operating coordinate system. Okay, so this would be Vy prime and Vzb prime. So this is my new coordinate system. Okay, so so we've got all of these derivatives that we need to rotate. And so for example, we could look at the first ones here. The derivative of x with respect to u. Now, there's just one kind of trick, I guess, when we look at rotating these, and that is that we actually have two things. We have to rotate this twice. So let's just take this guy, for example. So we'll look at fxb, and actually I'll just write this in another notation, so it's just a little bit quicker to write. So fxb comma u, and because of symmetry, we dropped some things in that. We're going to look at this tensor here for a second. So we dropped several of these. In fact, we dropped all of these and all of these. So what we're left with is fxb comma w there, 0, 0, 0, and then fzb comma u, 0, and fzb comma w. Okay, so I would like to know what those are in my prime coordinate system, or my new coordinate system, and it's going to depend on what they were originally. Okay, so I've got let's see, this is going to be fxb u 0, fxb w 0, 0, 0, fzb u, and fzb w. Okay, so what we're trying to do now is rotate these derivatives and get the derivatives in our new coordinate system, where I've put a prime up here to denote that new coordinate system. So it turns out that we actually have two things we need to rotate here. One of those is the force in the x direction, or the force in the z direction. So it's the direction of this force. The other is the derivative. See, this is a derivative with respect to u or w, and it turns out that u, v, and w are slightly different, or are also rotated in this new coordinate system relative to the original coordinate system. So, so we actually have two things that are being rotated here, and so I won't work through this in detail. But what you end up doing is pre-multiplying by that matrix there, and post-multiplying by the by that matrix transpose, okay? So we actually end up doing two matrix multiplications on this tensor of derivatives, and you basically repeat that for each of these derivative tensors up here. Okay, now it is actually different for this final tensor with respect to our control surface deflections, and that's because our control surface deflections do not they're tied to our aircraft in a way that their coordinate system doesn't change with a change in stability coordinates. Okay, so where UV and W, the directions of UV and W, U dot, V dot, W dot, and PQ and R would change with this coordinate system change, the control surfaces do not, and so you end up only, I believe it's you only pre-multiply these final two matrices instead of including this post multiply for the second term there. But anyway, so that's how we get this. That's how we rotate things from one coordinate system into another. And what I've done is I've just typed up what these are in non-dimensional form. So let me just drop those on here, and actually I'm going to put them on the next page here. So these are all the coefficients that we need. Let me just scroll back up for a moment though and just point these out. So these are our original equations, our linearized equations of motion here. And you see all of these derivatives that we're going to need, like CD mu hat, CD alpha hat, CL mu hat, CM mu hat, CM alpha hat. So all of these aerodynamic derivatives. And we have those in our original coordinate system, some coordinate system where we got that information. And now we want to rotate those into a new operating stability axis coordinate system for our operating condition. And so following this method here, this is how we would get the new derivatives. So for example, the new CD mu hat, see I've got primes over here on the left hand side. This represents all of the new information in the new coordinate system. It depends on our original CD mu hat as well as our original CD alpha hat, as well as CL mu hat and CL alpha hat. Okay, so we would plug in the information that we have from our reference condition over here to get the derivative that we need at our current operating condition. Okay, so these are all of our drag derivatives up here. These are the lift derivatives here. We've got pitching moment derivatives here, change in y force derivatives here, change in rolling moment derivatives here, and change in yawing moment derivatives here. Okay, so one last thing I want to point out is if we come back here, there are a few derivatives that we actually that we plugged in a little bit differently than others. So usually we have these derivatives here like CL mu hat, CM mu hat, but for a couple of these, we actually took the derivative of that in terms of our aerodynamic coefficients, and we got, for example, this guy here is minus 2 CD naught. That's the drag coefficient at our operating condition. This is the lift coefficient at our operating condition. Here we've got lift coefficient operating, and then this is a change in drag with respect to alpha, a change in lift with respect to alpha, CD naught, and CM naught. So these 5 components right here we're going to treat a little differently than the others. All of these other derivatives, we know how to get those through this rotation. If we were given those in the reference condition, we can rotate those and compute them in the operating condition. But these 5 components here, we are just going to take directly from the new operating condition. So for example, we know what CD naught is at our operating condition, and that's because we know that drag is parabolic. So we've actually defined drag as CD0 plus CD1 times CL plus CD2 times CL squared. So we can actually get the drag at any operating lift coefficient. So if we just put a little O here and plug in our operating condition, instead of our reference condition, that will give us CD naught instead of the CD reference. Okay, so that's our, so we'll just plug that in directly, and that shows up in a couple places here. So this CD naught here, that CD naught there. We don't need to necessarily rotate those from another coordinate system. We're just going to compute that directly from our equation for drag. Okay. The other thing is CL, so we need our operating lift coefficient. Well, that depends on our operating weight, our climb angle, theta naught, and divided by 1/2 rho v naught, our operating velocity, times wing area, and also we can divide by a cosine phi naught if we have some operating bank angle. We'll get into that later, where we could be trimmed in a coordinated turn, and so we could have some bank angle. So so for this aircraft, and actually I guess we could plug in a W naught there, for our operating condition, we're given a weight, a velocity, a climb angle, and a bank angle. And from that, we can compute our operating lift coefficient. Okay, now that may be different from the reference coefficient where we got all of our aerodynamic information. And so, and basically, what this lift, well, this lift then is going to be plugged in here to get our operating drag. And this lift coefficient is also helpful for us to actually figure out how much to rotate from the reference condition to the operating condition. Because if we assume that the lift slope is constant across this, then as we change angle of attack, then the angle that we need to rotate to get from the reference condition to the operating condition is just equal to our CL ref, our reference lift coefficient, minus CL naught, our operating condition, divided by CL alpha. Okay, so this is kind of an important relationship right there. So if we're given some reference, so at some reference condition here, we know what the reference lift was when we got all of these aerodynamic derivatives, and we know what our new operating condition is, then we can take the difference between those two lift coefficients, divide by the lift slope, and that gives us, and that will give us the angle that we need to rotate to get our coefficients from our reference condition to our derivatives in our operating condition. Okay, so so we've gone over, let's see, each of these now. We know how to get CD naught, CL naught, CL naught, CD alpha. Actually, CD alpha is just the derivative of this with respect to alpha. So we can get that directly in our operating condition. We don't need to take any information from the reference condition. And then lastly, we're going to assume that CL alpha is constant. And so we can just use the CL alpha that was given to us at our reference condition. And we're going to use that actually right here to compute our change in this angle for our stability coordinates. But anyway, so that's also just a constant that was given to us. So hopefully now you see that this information, when we have information given to us in one coordinate system, we can actually transfer all of those derivatives, all of that aerodynamic information over to another coordinate system. And by the way, that's also true for the inertia tensor here. So all of these inertia values also need to be rotated from one coordinate system to the other. And so we've got equations for that as well. And so anyway, that should help you understand how to rotate all the aerodynamic information, all the aircraft information we need from one coordinate system to another to build out, to fill out these equations now in any operating condition of the aircraft. Finally, let me just drop the equation for that inertia tensor on here as well for the rotation of the inertia tensor. And that's right here. I'll just drag this right down here. So this is, if we have the inertia tensor in our original body fixed coordinate system, then we can get the new inertia tensor IXX, YY, ZZ, and XZ in our in the operating coordinate system, or in our new stability coordinate system. Now, of course, this does assume that the inertia tensor is symmetric about the XZ plane. Okay, so this is neglecting any rotations of those of the off-axis inertia components, except for XZ. XZ can be non-zero for a symmetric aircraft.